Okay, thank you very much. So here's the general situation that I'd like to talk about. So we have a finite dimensional real vector space V and a convex body, by which we mean a compact convex set. And most of the time I will not be talking about convex bodies as such, but I'll be talking about some particular convex bodies, actually about 3 different convex bodies here. And the features of these convex bodies would be as follows. So the dimension will be quite high, though finite, so it will be hard to draw a picture. And that's what's called the membership problem. So the simplest question you ask about a convex body. So if I give you a point, can you decide whether this point lies in the body? This question will be very hard to answer. So these convex bodies will be kind of evasive, so hard to get our hands on them. And the question will be, what do they look like? Well, can we draw something? Can we infer something about those convex bodies? And of course, there is always this nasty question, so why do we care? And I know it's very hard to explain, because once you sort of build a chain of thought, so we care about this because of that, then the next question comes, why do you care about that, and so forth. So I'll try to answer these questions in the course of the talk, but I will not be surprised if after the talk, so people will ask, well, so what? So why do you care? Yeah, here's the first example, which often one of the most famous examples in combinatorics and optimization. So it is traveling salesman problem, polytope, I'm sorry, and it exists in 2 main versions. So here is a symmetric version. So you fix a complete undirected graph with n vertices, and then you look at the Hamiltonian cycles in this graph. So it's a closed path that visits every vertex exactly once. So there will be, since the graph is undirected, so it will be quite many of them. So n minus 1 factorial over 2. And for each such a Hamiltonian cycle, we introduce a matrix that just encodes it as a point in the space, which has 1 if 2 edges are connected, and 0s if they're not, and take the convex hull of those things. Now, that's the traveling salesman polytope, so it often appears in optimization. Now the question to the audience, what does this chart have to do with the polytope? What it's supposed to represent? So what if I say that the number is boxes is the same number n than the number of vertices in the graph? So this is a Young diagram of the representation of the symmetric group, which is used to get this polytope. So if you take the representation of the symmetric group as this Young diagram, take a special point, take the orbit, and take the convex hull, then you get the traveling salesman polytope. So that's what it stands for. Okay. So there is another version of it, the asymmetric version. It's pretty much all the same, but instead of the undirected graph, we take the directed graph and we look at all directed Hamiltonian circuits, and we encode them again by n matrices, take the convex hull, and then it has n minus 1 factorial versus a little more because of the direction starting to matter. Here's its dimension. And then the question is what these 2 things stand for. And those are irreducible representations of the symmetric group, so that if you take the direct sum of this and take a special point, namely this cycle, right, and rotate it by the group and take the convex hull, that's the polytope you get. Right? That's another example. And as you see, well, the membership problem and optimization problem, they're, as we know, equivalent, and they're both hard in this case, and p-hard. So if I give you a matrix, it's pretty hard to tell whether it's in this polytope, or it's pretty hard to optimize a linear function on this polytope, right? But the example I'm truly interested in is this following one. It's non-negative polynomials. So you take choose two positive integers k and n, and consider the vector space of all real homogeneous polynomials of even degree 2k. And the degree is even. That will become clear immediately why. So, and in this space, you basically consider the set of polynomials that are non-negative everywhere. That's why I need the even degree. Right? And I want to make a body, so it's not compact yet. So if I normalize it, if I require that the average value on the unit sphere is 1, then I get the proper convex body. So I get something, right? I get the convex body. It's a convex body of all non-negative polynomials. And I sort of care what it looks like, right? And now it may become a little bit more clear. So why do we care what convex bodies in high dimensions looks like? Well, because they often, we stumble upon them. So these two come from optimization, and this two is basically a fundamental object in solving systems of real polynomial equations. Actually, solution of any system of real polynomial equations can be reduced to testing non-negativity. So you give me a polynomial and ask me, so does it belong to this convex body? Right? That's a membership problem. And it's awfully hard unless k is 1, which means that we're dealing with quadratic forms. Okay. So in other words, we deal with these problems, sort of to steal a sentence, right? Not because they're easy, right, but because they're hard. So, and let me put some observations sort of to here that sort of summarizes the convex bodies we are working with. So they're given by concise word description. So I'm just talking for a little while, and then it's completely clear what I'm talking about. But at the same time, it's not clear. Nothing is clear, right? So you look at these polytopes, or at this polytope, or this convex body, and it looks back at you. And while you sort of get acquainted with each other, you don't really know what to do with it, right? So for example, the traveling salesman polytopes are interesting. Yeah, because optimization on them is interesting, and they defined as convex calls of many points. So in a few words, in like less than 3 minutes, I managed to define n factorial points, right? Right? And the body of non-negative polynomials here, it's even worse, is defined by infinitely many linear inequalities, because what I require for any point in Rn or in the sphere, I require that the value of this polynomial is non-negative. That gives me a linear inequality in that vector space, right? So I get a convex body defined by many, many, many linear inequalities. And I sort of care what it looks like. And here the membership problem is interesting. So given a polynomial, decide if it's everywhere non-negative, right? So we can ask, so do they look like this, or maybe that, right? And this is not a completely outlandish picture, by the way, for a convex body in high dimensions. So people quite often, more often than not, draw a high dimension sphere this way. So why is that? That's because as the dimension grows, the bulk of the volume of the sphere is concentrated near its hyperplane section, right? So take any equatorial section. As the dimension grows, all the volume is pretty much concentrated there. And that's what it's supposed to represent. Of course, it doesn't represent that you can take any hyperplane section. It will still be concentrating around it, right? Here's only 2. But it sort of gives you a hint that things may be quite counterintuitive there. Okay. So that's the scope of problems I'll be trying to describe. So now let's do some, for a change, let's do some general theory of convex bodies. It will be very short. So the simplest convex body is an ellipsoid. And here I definitely, my combinatorial colleagues would disagree with me because people in polytopes think that the simplest convex body is a simplex. But I think it's an ellipsoid. It's just, from an analytical point of view, it's just an affine image of a ball. So, and ellipsoids are more fundamental than balls, because to get a ball, you need at least to have a scalar product of some sort. But to get an ellipsoid, you need nothing but the vector space. So if you change the scalar product, then the ball is no longer a ball, but an ellipsoid is still an ellipsoid, right? So, and then there is a remarkable result by Fries John in the 60s, so 20th century. So it says that every full-dimensional convex body contains a unique ellipsoid of the maximum volume. So the punchline here is not that the maximum volume of the inscribed ellipsoid is unique. That's quite clear. But the punchline is that the ellipsoid with the maximum volume itself is unique. And then it takes some care to approximate the convex body. So if you think of the origin being the center of the ellipsoid, then if you're inflated with a coefficient equal to the dimension, then it will contain the convex body, right? And if the convex body is centrally symmetric, you can do even better. You can inflate it with a coefficient that's just the square root of the dimension. And various ramifications exist. So if the convex body is kind of symmetric, not entirely centrally symmetric, but somewhat symmetric, then you can improve this bound. So, and these two sketches are supposed to represent the proof. Okay, so my sketches, I'm sorry, they not very good. I have a very narrow desk in my place where I'm staying, and whenever so my elbows always slip, and so the drawings partly represent this feature. So here's how we prove this inclusion. So we say that, okay, we can think of this maximum volume ellipsoid as just being the unit ball. Just choose the scalar product so that it's the unit ball. What I want to show that there are no points in the body very far away from that ball. Well, suppose there is, right? Then the whole chunk here, because of the convexity, is in the body. And I can sort of start shifting that ball towards that point. And at some point, namely right in the beginning, I'll get an ellipsoid of the larger volume, right? So in particular, if this point were sort of infinitely far away, then I would have gotten just a parallel strip here, and I can inscribe as large ellipsoid as I want. So, and that picture is supposed to represent the proof of the second inequality, and also show why symmetry is important here, because here, if I have a point far away, then I have a point far away but in the opposite direction. And I can start inflating ellipsoids sort of both ways, and I can reach contradiction sooner, right? So that's why we have the square root of the dimension. So there is another theorem of this sort, which looks sort of deceptively similar, deceptively dual. It's not quite dual to that. So it says that if you have a full-dimensional convex body, and if then it's contained in the unique ellipsoid of the smallest possible volume. So among all ellipsoids which contain this body, there is a unique ellipsoid of the minimum volume, and the same basically inclusions hold. So generally, if you deflate your ellipsoid by the factor of dimension, then you get something inside. And in this case, by the square root, then you get something inside. So it's pretty immediate to see that all these factors, dimension, square root of the dimension, one of the square root of the dimension are the best possible in general. So think of a simplex, octahedron, cube, and that's where you get this all the bounds attained so sharply. You cannot do really better. Okay. So one philosophical remark here is that the ellipsoids, the maximum and minimum volume, they're pretty basic. They don't really depend on anything again. They're just associated with the convex body. So if you change the scalar product, for example, then all the volumes get scaled, right? But the largest volume stays the largest, and the smallest volume stays the smallest. So the ellipsoids do not change. So they don't, unlike many other remarkable ellipsoids, this particular do not depend on the structure of the ambient space. They are intrinsic to the convex body, right? And they capture some general information about our convex body. Okay. So a couple of words about the names. So these ellipsoids often called John ellipsoid, Loebner ellipsoid, Loebner-John ellipsoid, Loebner-John Barrington ellipsoid. And this history, as is with all good notions, is very complicated. I don't understand it quite well myself, but I think John discovered Loebner ellipsoid, and Loebner discovered John ellipsoid. I think that's what happened in the end. That's why I stick to this notation, maximum minimum volume. Right? So if trying to avoid the controversy here, right? So then, let me ask a question then. So how to find those minimum maximum volume ellipsoids, because that looks like a natural first step in dealing with convex bodies, just to get a general shape, right, of the body. So one observation, that the bodies we care about have rich symmetry group. And I have a sort of philosophical explanation of that that you may or may not accept. That if you look at this convex body, they described in one paragraph. And if you make a general sentence, not very long, like about something very general, like all people, or well, the weather in California, such and such, then whatever you're going to claim is ought to have large symmetry, right? Large symmetry group. You will not distinguish between various peculiarities, right? The general statements apply to preserve symmetries, right? So, or in other words, it's hard to break symmetry in few words. So the fact that the convex bodies we are dealing with have many symmetries is, I think, it's a rule rather than an accident, right? So, and let's try to capitalize on that. So that comes a less philosophical, but still quite a philosophical observation, that if you have a group of isometries acting in your space, so I already assumed that there is some scalar product there, and your convex body is invariant, then the ellipsoids must be invariant. And that's clear because they're unique, right? If they were not, then you get the ellipsoid of the same minimum maximum volume, but different. So they must stay invariant. It's very good. Yeah. Refinement, that suppose that the action is irreducible, which means that there are no proper invariant subspaces, that the only proper invariant subspace is the origin and the whole space, right? So there's nothing else. Then both ellipsoids should be balls. So why is that? The ellipsoid is defined by quadratic inequality. And if you look at this quadratic form, then you see that if the ellipsoid is invariant and the quadratic form is invariant, then its eigenspaces are invariant. But there are no proper invariant subspaces. So there is only one eigenspace. There is only one eigenvalue. So it has to be the identity. So it has to be a ball, right? So we can build on this and look at the symmetric Chern-Salzman problem and ask ourselves, so what would be the ellipsoids associated with this polytope? So So as we know, there is a huge symmetry group here. And it's the symmetric group, which acts in the space of matrices, the ambient space as a polytope lives, by simultaneous permutations of rows and columns. There's also a pretty standard invariant scalar product, which you just multiply, take the scalar product of matrices in the usual way. Right? What is nice about this example is that the representation, if you restrict it to the affine span of the polytope, where it exactly lies, is irreducible. So the only invariant affine subspace is the center of the polytope, just a matrix that you have zeros on the diagonal, 2 over n minus 1 everywhere else. There's nothing else invariant there. That's why that diagram comes into play. So it's irreducible, right? Therefore, both ellipsoids associated with this thing have to be balls. Right? So in particular, the minimum volume ellipsoid also has to be a ball, and it has to contain, it's better to contain its all the vertices of the polytope on its surface. Right? Otherwise, we can push further, and we know the center. So we get for nothing just the minimum volume ellipsoid. So it's a ball in the affine span of the polytope, and the affine span is pretty easy to figure out. It's a space of symmetric matrices with zero diagonal row and column sums equal to 2. And the radius of this ball is this, right? And so from this, by the way, from John's theorem, we conclude that if we shrink this ball by an appropriate factor, which is a dimension, then we get a ball of this radius sitting inside. And here's a question. So what's the maximum volume ellipsoid looks like? What is the radius? So we know that it at least this much, but it may be slightly bigger, not much bigger. And the interesting thing, well, for me about this problem, that I don't really have any feeling how hard it may be. So we got some bound. But we did nothing, mostly sort of hand-waving. So maybe if we work harder, we get something better. So some people worked harder, but I don't think they got much better. So I don't really know. Right. On the other hand, if you think about this traveling salesman, it shouldn't be very complicated to figure out what's the largest ball contained in it. But somehow it's, well, it's not immediate. Right. Yeah, you don't know the facets, but somehow, well, you know what we are talking about, right? All these Hamiltonian cycles. Yeah. You know, some facets, maybe those will be enough. Maybe not. Yeah. All this kind.
Have you looked at sort of the known facets and how far they cut in?
Yeah, they kind of, yeah, I looked at some, and some cut farther than I sort of indicate, yeah. But frankly, I didn't look this close at that. I looked at some papers which studied this question, and as I understand it, it's still not resolved. Yeah, so I just wanted to show that hand waving plus symmetry basically gives you something out of nothing, which is already something, right? Out of nothing, right? So let's go to the case of the, let's see, of the situation when the action is actually reducible, when there are there are invariant subspaces. Let's consider the following interesting situation. So you have a space, and you have a group acting in this space, a compact group. But, yeah. You take a point. You rotate this point by the group. You take the orbit, and you ask all sorts of questions about ellipsoids. And here is a result by Grigory Blecherman from the University of Michigan, and the result says that you can do that. It says that there is a decomposition of this space into irreducibles such that the ellipsoid, the minimum volume ellipsoid, is given by such and such formula. Right? So what this formula says, well, you sort of know that this ellipsoid ought to have symmetries. So its eigenspaces ought to contain some sums of irreducible components. And this is the exact formula. And it almost gives you what do you need? Almost. There's one exception if this representation is not multiplicity free. That if there are some non-isomorphic components, then the decomposition is not unique. Then you have to do something, and that something really doesn't matter. This is the part of the theorem that belongs to me. So it's not relevant here because it will pop up in a different place in much nicer form. Okay. So with this in mind, let's go back to the asymmetric travel salesman polytope. So that's there. The action is reducible. It's actually quite somewhat reducible. So if you look at the affine span of that polytope, then there are two irreducible components there. So one roughly consists of symmetric matrices, and the other roughly contains of asymmetric matrices. You can remove roughly if you say that the diagonal must be 0, and row and column sums must be 1s. And then if you apply this result, that's a multiplicity-free case, when you get just a formula. I sort of computed it for fun. I think no one did that before. But that's a formula for the minimum volume ellipsoid for the traveling salesman, asymmetric traveling salesman polytope. And it's not a ball. It's almost a ball, but it's not quite. It's slightly tilted or kind of stretched towards skew-symmetric matrices. So if you think you can speculate saying that asymmetric traveling salesman problem is somehow biased towards skew-symmetric matrices, that even sounds like a pun, but yeah, it has some sort of a background explanation that the ellipsoid that you get is not really ball, right? It's slightly stretched. Okay. Right. So as I said, that the second part of this theorem is not really important because it pops up in a dual situation much nicer. And this is a result of myself with Gregory Blecherman. The history of the result is that I tried to understand his proof of what turned out to be a simple application of this result. And I couldn't. And no matter how many times he gave me a simplified version, I still couldn't understand it. And so finally, we got this, which I think is reasonably simple in general. So it says that if you have a finite dimensional vector space and a compact group acting there, and you take a point, and you take the convex hull of what you get if you rotate this point around by the group. Now, you look at the polar, and the polar consists of all linear functionals whose value does not exceed 1 on the whole body. And you ask a strange question. So what's the maximum volume ellipsoid inscribed in that polar may look like? So the reason you want to ask this question is twofold. First, there is a very simple answer. And second, there is, I think, a nice application that I'll show you in a moment. So the answer is as follows. So the maximum volume ellipsoid inscribed in the polar of the orbit is defined by this formula. So it consists of all linear functions such that it's the average square on the group of the linear function on the orbit doesn't exceed one of the dimensions. So it's a quadratic equation. So it's it's a ball in L2 norm, roughly, right, in some sort. Right? Okay. So, and it is true no matter what space you take, what point, what representation. Yeah, probably I ran out of parameters. The only thing that you require is that the body you get is a full dimensional, so you can talk about the polar here and the ellipsoids. So an immediate application to that will be to compute the maximum volume ellipsoids of this convex body of non-negative polynomials that I talked about, right? So what it says here, yeah, remember that we define this convex body as the set of all polynomials that are non-negative everywhere and has average value on the unit sphere is 1. So it's kind of a weird-looking thing. And it turns out that it has a very nice maximum volume ellipsoid. So to describe it, you have to introduce, of course, the scalar product, which is just the integral on the sphere. So you make it Euclidean space now, the integral of the product of two polynomials on the sphere. And inside that convex body, there is a particularly nice polynomial, which is sum of squares to the k. It's just a center. And it happens that the maximum volume ellipsoid of this set is just a ball centered at this polynomial and of this precisely radius. Right? So there is a ball sitting inside this convex set of non-negative polynomials. All right? And it's the maximum volume ellipsoid. It touches the boundary. You can figure out, by the way, exactly where it touches the boundary. So there will be some peculiar polynomials, Legendre polynomials, associated with the tangent point. So this result is also Grisha-Blecherman. And then there is a question, so what would the maximum volume ellipsoid, minimum volume ellipsoid look like? So if you try to enclose this set from the outside, and you can get some estimates through John's theorem, right? And basically, as of now, we understand the asymptotics more or less okay of the radius. But we don't have any exact answer for the sort of outer ellipsoid, the minimum volume ellipsoid. Or we don't even know if it's a ball. It has no reasons to be a ball. Because the action here of the group, which is orthogonal group, is very much reducible. So, and for this problem, for this question, I have a feeling that it's a hard one, because somehow it's hard to enclose non-negative polynomials into something. So it's much easier to round them up from inside. Right? Yeah, and here's a simple explanation how these two things are related. How these two things are related. So the explanation is that this set of non-negative polynomials is nothing but a polar to the orbit. Okay, so that sounds nice, but so to construct the orbit, you need at least a group, a space, and a point. Yeah, so here's the group is the simplest. It's the orthogonal group of all orthogonal transformations of Rn. So here's a space. So you take the tensor product of Rn with itself 2k times. So 2k is the degree. So you get a space of dimension n to the k. So here's the action. So orthogonal group acts in each component separately, and it's just a tensor power of its sort of regular action in Rn. Here's a point. You take say the unit vector in Rn, tensor it with itself 2k times, And now what happens when you rotate this point by the orthogonal group? You get a bunch of tensors that looks like a unit vector tensored with itself 2k times, right? So as you go around, right, as you apply orthogonal transformation, so you get all possible points of this type, a unit vector tensored with itself k times. So it's some tricky surface there. But then things starting to sort of to turn your way, because when you ask yourself, what's a polynomial of degree 2k anyway? Then you answer yourself that it's just a linear function on this x tensored with itself 2k times. And when you ask yourself what's a non-negative polynomial, well, it's a linear function that's non-negative on this particular thing, right? And if you normalize it by the condition that the integral is 1, then precisely you get the polar. So I think it's a very good view of non-negative polynomials as being polar to the orbit in the action of the orthogonal group. It's a tautology, but of the sort that I think makes some things a little clearly. So with this in mind, we immediately arrive to this result.
So just k equals 1 is the positive.
Yeah, quadratic forms.
So is this known?
Yeah, well, I don't know, but it's an exercise in the book I wrote. So yeah, for quadratic forms. Yeah. There's one question here that I'd like to ask. So I know of no other applications of these marvelous results other than this. So if you can think of others, so please let me know. So this result was sort of brought up to explain, to give a simple explanation of what's going on here, why the ball of the largest volume inscribed in a set of non-negative polynomials is precisely this thing. So the original proof by Blechermann used zonal polynomials and many, many constants and special functions that somehow managed at the end cancel each other. And I certainly believed him, but I could never track down these cancellations. So why do they cancel each other this way? So that's worked as a substitution for a computation. So if you can think of a different example. Yeah?
Have you looked at the exterior power rather than the symmetric?
No, that might be. Yeah, thank you. That might be another. Right. Okay. It's probably time to switch gears and then.
I was asking because in Federer's book on integral geometry,
Uh-huh.
they talk about calibrations on Grassmannians.
Uh-huh.
Might be useful.
Right. If you take the Plicker embedding of the Grassmannian convex hull, right?
Convex
Huh.
hull Grassmannian.
And that's, well, people did stranger things, but we can do that.
There was a whole conference about that 2 weeks ago here.
About taking the convex hull of the Grassmannian? Oh. Sorry I missed that. Right. Okay. So here's a question. What can be the next step? So far we played with ellipsoids with some success, limited though. But, and then we can ask, so can we do any better? Yeah, so ellipsoids give you a quadratic hypersurface, but you'd like to have a maybe high-dimensional hypersurface can give you a better approximation, and that's very much in spirit of computational geometry. And here I restrict myself to symmetric case, and I tell you frankly why. Because it's easier. Yeah, there's some things going on in non-central symmetric case, but they don't look awfully nice, to be sure, right? So also with central symmetric body, you can associate a norm. So you can measure norm, right, the gauge function here. And then the question comes, how do you approximate the norm by a root of a polynomial? So all these things about ellipsoids essentially tell you that if you want to approximate a norm by a root of the quadratic form, then you can get this good. So you can get a factor square root of the dimension. And this is the best you can do with some particular norms. So you cannot do better, right? But maybe you can do better with polynomials of higher orders. And indeed you can. And here's the result, which I proved some time ago. So what it says that if you take any essentially symmetric convex body, full dimensional, well, it doesn't really matter. You associate a norm with it, then for any integer m, there is a polynomial homogeneous of degree 2m. You always need, of course, even degree, which is everywhere non-negative, just like a quadratic form. And it's actually a sum of squares, and which satisfies a strange-looking inequality. So it kind of pinches your norm from below and from above. And for all practical purposes, whatever this sentence may mean, right, it behaves roughly like a square root of the dimension divided by m. So as m grows, as you afford the polynomials of a higher and higher degree, then you get a kind of a better approximation. So the approximation factor converges to 1 as soon as the ratio, the dimension over the degree converges to 0. So if you want a constant factor approximation, you get the degree proportional to the dimension. And if you want something that's sort of asymptotically tight, you get a degree that grows faster than the dimension. So for example, if you care about approximations of the roots of degree 4 from a quartic, from polynomial of degree 4, so you get something like that. You get square root of the dimension divided by root of degree 4, right, of 2, which is strictly greater than 1, which is nice. So you can do better, strictly better than by quadratic forms. And there is a whole bunch of questions arising here, which some of them I can answer and some of them I cannot. So clearly, or almost so, that with every convex body we can associate the best, say, approximating polynomial of degree 4. That's a polynomial that cannot do better than that. And then we can ask, what's the worst possible degree of approximation we can get, right, over all bodies in that particular dimension? What I definitely know that this constant has the sort of asymptotic value of the constant, non-zero constant times square root of n. So you cannot do better than some constant times square root of n with degree 4 polynomials. But I don't know the constant. Right? So I know that the constant is less than this one, but maybe it's 1 over 1,000. That would be much nicer, of course. Right? I don't really know. Also, it's somewhat tricky. So the proof of this theorem that I have is somewhat is very simple, and it stubbornly gives you the best approximation polynomial. Although when you look at the proof, there is no reason why it should, and indeed it really does not, right? But the example where it does not give you the best approximation polynomial is not very immediate, but I think I'll present it at the end. Also, what you can say that this best approximation polynomial, maybe not unique, that I don't know, probably not, but it sort of can be constructed with various invariant properties. So it can be constructed preserving symmetries and such. That's roughly because the set of best approximation polynomial necessarily convex. So you can take their convex combinations of their powers, rather. What's embarrassing is that what I don't really know. So far we were approximating norms by at least convex functions. And I don't know if this thing always comes out to be convex. So in the examples that I computed, it does. But on the other hand, I think it's even nicer if the best approximation of the convex body by degree force hypersurface will be by non-convex hypersurface, right? That would tell something about the boundary of this body, that somehow the convex body has such sharp angles here and there that this hypersurface wants to avoid them at any cost, even at the cost of becoming non-convex, right? That would make perfect sense, but whatever you say to the opposite would also make a perfect sense, right? so I don't really know the answer here. Yeah. I think I'll sketch a proof because it is easy. So it fits one page. So what we do, we look at the polar of the convex body, and it's some other convex body living in the dual space. Then we use the duality argument to say that the norm associated with the convex body looks like this. So we take all linear functionals from the polar, compute it at the point, and take the maximum. Right? That's precisely why the duality theorem is precisely the norm. Then I say that if I raise this to the power m, and suppose for simplicity that m is odd, then nothing changes. So the m's power of the norm is just the maximum of m's power of this thing. Then I do something also tautological. I say that if I go to the tensor product, I can write it as a tensored functional with itself applied to the point tensored with itself. Right? Then I can take the convex hull of all these tensored functionals, and it will be some convex body. So what I say that the m's power of the norm is just maximum of a linear function from some high dimensional convex body applied to the tensor power of x. Then I say that I can approximate that convex body by an ellipsoid. And notice that this is exactly the square root of some polynomial. So that polynomial that I want here actually emerges. But then a question arises, so why doing something tautological I get a gain, something better than 1 at the end. And the reason is a dimension argument, that the dimension of this convex body is not as large as they think it is, because this convex hull of tensor powers lives in the symmetric part of the tensor product, right? And the dimension of the symmetric part is smaller. It's the binomial coefficients. So therefore, from John's theorem, I get a gain. So, and from this construction, you see that it respects all the symmetries, and it actually carries over orbits and everything I've been talking so far. So it's OK. Right? Okay. Let me give you some examples. So how to approximate, maybe how not to approximate, how to approximate norms with polynomials. So, OK, so we have an n-dimensional cube and an octahedron, n-dimensional, and the two norms. One is L infinity norm. Another is the L1 norm, which I don't know, I didn't write it here. So when we try to approximate these norms by square roots of quadratic forms, there's no difference between the cube and the octahedron. So the best we can get is the square root of the dimension. And that's the approximation we have here. But something interesting happens, and it has something to do with geometry, but I don't really know what part of geometry. So if you try to approximate by polynomial of degree 4, then octahedron shows its clause, right? So it cannot be approximated better than some constant times square root of the dimension. While cube behaves rather nicely, that you can get a factor n over 1 over 4, which is much better, because you just approximate by the L4 norm. And you can, that's provable, that for the octahedron you cannot get better than constant for the times the square root of the dimension. Sort of in the retrospect, in the hindsight, it's sort of clear that the cube is kind of round. So if you try to fit a hypersurface inside, well, you can get closer to corners somehow, right? And octahedron is kind of sharper. So if you try to fit a hypersurface there, then you'll get stuck, right? And that's what this constant here says, right? You can't really do better. But it would certainly be pity to develop all this theory just to obtain these two formulas, because that you can get anyway. So here's some other example, which I think provides some food for thought. So it's sort of a symmetrized version of that convex body of non-negative polynomials. So what it says, so I consider this space of homogeneous polynomials of a given degree d in n real variables, and I consider the convex body in the L infinity norm there. So all the polynomials whose maximum value on the sphere, absolute value, doesn't exceed 1. That's sure thing. That's a pretty wild-looking convex body, right? But then we can approximate it, and not surprisingly, the theorem gives us that this L infinity norm must be really approximated by LP norm, right? So you have a standard approximation here. Here you have some factor that again converges to 1, not too fast to be sure, but not embarrassingly slow also, as you increase the degree of the polynomial, right? So you can pinch on polynomials, you can pinch L infinity norm by LP norm with some bounds. This bound is, by the way, asymptotically in some sense, reasonably strong sense. It's asymptotically optimal. So you cannot do better with L infinity and LP norms on polynomials, because if you take the powers of linear functions, that's there you'll get your bottleneck here. But it doesn't mean, of course, that there cannot be another polynomial, not just an LP norm, which does the thing better. And here's the example I was talking about. The theorem doesn't give the best possible construction. So if we are talking about quadratic forms, so the norm we are talking about is the maximum value of the quadratic form on the unit sphere. And that can be approximated pretty well by polynomials of high degrees, much better than the square root of the dimension, actually, with this particular factor, for the reason that the maximum value of the quadratic form on the unit sphere is just the maximum absolute value of the eigenvalues, right? So what are you doing? You approximate the maximum absolute value of eigenvalues, but those you can approximate by powers, right? By LP norms on the eigenvalues. But LP norm on the eigenvalue is a polynomial in the matrix, right? Because this expression, the sums of powers of eigenvalues, is just a symmetric polynomial. So it must be a polynomial in the quadratic form, right? So for quadratic forms, we can get a much better deal. So question here, that is it something that we just don't see on polynomials of high degree, or is it something that doesn't exist on polynomials of high degree? So can we get a better approximation on polynomials of higher degree by taking some peculiar polynomials on those polynomials? Or there's nothing better than just the old LP norm or equivalent? So these are the this is a question. And again, I really don't know an answer to that. And I don't really have a feeling what the answer can be. So for example, maybe for cubic polynomials, you can do better than LP. But somehow for polynomials of degree 4, then everything is lost forever. Right. So I think I have, how many, 2 minutes? Yeah, OK. Yeah, so what I'd like to say in the remaining 2 minutes, so that my second talk, I'd like to talk entirely about this convex body of non-negative polynomials, because I think we all complain about lack of examples, and this is the very good example, this convex body of non-negative polynomials right here. And there are some quite remarkable recent developments, so the latest of which came in the email today morning. So we understand what it looks like reasonably well, I think. And it does look, on the one hand, it does look beautiful. But on the other hand, it certainly looks as ugly as it probably can get with convex bodies. So, because that's probably if you want something that really bad but convex, so you should go with this, I think. It's this universal convex body that accumulates all the singularities there are. Okay. So in the remaining 30 seconds, I'd like to at least put up a slide with other interesting issues. And here it's not intended to mean that what I was talking about was interesting, but it's rather interesting issues of other kinds. And it's approximating convex body by epsilon nets, and basically the punchline that you need exponentially many points if you want to do it any reasonably well in high dimension. And then a very well, not very recent, but quite a remarkable development by Ben Tal and Nemirovsky. So what if you approximate something convex by projection of a polytope with a sort of a reasonably small number of facets? Because if a polytope in high dimension has a small number of facets, it can have an awfully large number of vertices. And the question is, can you fit this projection so that those vertices coming in multitudes sort of approximate your body very tightly? And they've shown that this is so amazingly tight approximation for the usual Euclidean ball that to approximate the ball n-dimensional with an error epsilon, you should go only this high in the dimension of the polynomial and the log epsilon inverse in the dimension of the ball, and take a polytope with this many facets. And when you squish it down, it nails the ball with an error epsilon. It's really remarkable. And the other remarkable thing that it's actually very practical, because Nemirovsky explained that in Haifa they had a linear programming solver but didn't have a quadratic programming solver. And they wanted to reduce quadratic programming to linear programming. And that's precisely how they did. So for that, you just need to approximate sphere by projection of a polyhedron. And that's exactly what they did. So I didn't talk about approximation on average because it's not intrinsic. It's extrinsic. So what a convex body looks like if you apply an average or your typical objective function or something like that, look from your typical direction. It's extrinsic because it relies on the metric of the ambient space. And if things become intrinsic, they certainly change completely. So for example, from the extrinsic point of view, the traveling salesman polytope looks like a Euclidean ball of radius square root of 2 log n. So if you take a random linear functional, on the asymmetric Salomon problems. So, and optimize, it's just the same as you optimize it on the ball of this radius. So there's not much difference. So these problems on average are very easy, precisely because they're extrinsic. They involve some structure not related to the convex body. So, okay. This is it. So thank you very much. Yeah, the ellipsoids, it's also an exercise in my book. So there is no answers there, though. But yeah, you can compute both. Yeah, yeah, but it goes without a star or an asterisk. So it's a reasonable exercise, but not terribly hard. Yeah, you can compute those. Yeah.
So for the ellipsoids, you fit a different shape ellipsoid inside and outside.
Yeah, well,
but
yeah.
for quadratic or quartic higher degree things, you were taking the same one scale.
No, but eventually with ellipsoids, I didn't want both, right? I wanted one of them because I knew that if I get an inside, then if I blow it up, it will contain the whole thing. Or if I get an outside, if I shrink it, it will be contained in. So I was content to settle with either one of them. And in fact, with one that I can compute. Because it so happened that I can compute either the outer or the inner, but almost never, except a few simple cases, both. Oh, yes. Yes, I did, but it's sort of a separate thing. Yeah, it makes it easier to compute various LP norms, for one thing, because you know how to integrate things if you know the support. Yeah.
What can you say about the relation between the Löwner ellipsoid and the John ellipsoid? It's like there's no reason why they should have similar axes? Or?
There is no reason except so if you have central symmetric convex body, then you know that one is the polar to the other taken of the polar, right? Right? Because you know that their center must be in the origin, so everything is nice. But as soon as you have something non-centrally symmetric, then the centers of those ellipsoids start wander around, and they connect it only historically.
But I mean, things like situations where the centers would be far apart, or
how far apart they can be? Probably shouldn't be very far apart, I think, right? But they certainly can be different, right? Well, that's too complicated because there are two of them, and center there's only one. So.
Okay, well, thank you very much.
Thank you.